Hey, welcome to the fourth installment of IB Physics Thermodynamics. We're going to be looking at what it means to do work on a gas. We've been talking entirely about heat up to this point. And then we're going to look at something called the first law of thermodynamics. Now, if you have a container of gas, I'll say it's a cylindrical cylinder with a movable piston, and we'll say that the area of the base of this is A, that distance is x, the gas is in here, it has pressure P. Now let's say that we're going to compress the gas. To do that, we need to apply a force on that piston, and the force that we apply has to be equal to the pressure of the gas times the area, or actually there has to be a little bit more, but it has to be at least equal to the pressure times the area in order to make that piston move. And if we look at the work done, work is force times delta x, which is PA times delta x. Now if we look at the quantity A times delta x, so let's say you move it that far. A times delta x is the volume of this little area that's outlined in red, which is to say it's the amount that the volume is decreasing. So A delta x equals the negative of the change in the volume. And that means that when we compress a gas, work is equal to negative P delta V. And that's important because that's the work done on the gas. That's the work that the outside force is doing to compress the gas. And that will be a positive number if the gas is compressed. It will be a negative number if the gas is expanding. Because if it's compressing, delta V is negative, and that means work will end up being positive. So if the gas is compressed, you do positive work on it. Now the work done by the gas will be the negative of that. And that's actually a statement of conservation of energy. You should figure out why later. And so the work done by the gas is positive P delta V. And that will be positive if the gas is expanding. You do need to pay close attention to the on or by. You should remember that from last year, but just in case, it's very important and you need to know the difference. So let's say that we've got a gas, it's compressed from this to this volume at a constant pressure of 350 kPa. Find the work done by the gas. So since it's being compressed, the work done by the gas will be negative because it's being compressed. And so the magnitude of the work is P delta V, and P is 350 kilopascals, or 3.5 times 10 to the positive 5 pascals. Delta V is the final volume, 1.1 times 10 to the minus 3 cubic meters, minus the initial volume, 1.4 times 10 to the minus 3 cubic meters. And if you plug this in your calculator, that works out to be negative 105 joules. So very straightforward there. The work done on the gas will be positive 105 joules. The negative sign is important on the IB test. Usually if you leave off the negative sign, you lose the point. Now that equation, work equals pressure times delta V, only works if the pressure is constant. But usually when you compress something or expand, the pressure changes. And so you can't use this equation if it's changing. What you have to do is make a graph of pressure versus volume. We call this a PV diagram. We'll look at them a lot more in the next video. And as the pressure changes with the volume, actually it usually doesn't look like that. Usually it's going to be something like that. Let's say you are compressing from here to here. Now it turns out that the area here equals the work. Once again, if you're compressing, then you will deposit the work done by the gas will be negative, work done on the gas will be positive if you're compressing it, other way if it's expanding. For those of you in calculus, the work is equal to the integral of P dV. So that's what you do if the pressure is changing. There will be a question on the test where you're given that graph and asked to calculate the work. And our last thing is the first law of thermodynamics, also known as energy conservation. And it's a very, very simple idea. This delta U is the change in the internal energy. And basically what it says is that if we want the energy of a system to go up, we have to put more energy in. But we have two ways of making that happen. One way is to transfer energy by heat. The other way is to do work on a system. So Q is the heat added to the system. That's fairly straightforward. In this equation, W is the work done on the system. Sometimes you see this equation written as delta U equals Q minus W, but when people say that, what they mean by W is the work done by the system, not the work done on the system. Again, be very careful there. But it's very simple. Basically, it says that when you add energy to a system, the energy in the system goes up by how much you added. So it's not real profound. It's very, very useful, though. We'll see why in the next video.